In this video, we're going to talk about combining functions. So there's a couple of ways that we talk about combining functions. One way is in an arithmetic fashion. So to start with that, for function arithmetic, if we have f of x and g of x are functions, then we define f plus g of x as just the sum of f of x and g of x. So a sum of the outputs. So you can probably guess what the other arithmetic ones just from that one is, but let's just go ahead and click through them real quick. We define f minus g of x, or the difference of two functions, as the difference of their outputs, f of x minus g of x. Same concept for the product of two functions, f times g of x is f of x times g of x. And f over g of x, or the quotient of two functions, is f of x over g of x. So when we talk about the domain of each of these functions, we have to make sure that the x value can go both into f and into g. So the x values has to be in the domains of both of them, and we refer to this as the intersection of the domains of f and g. So the intersection of two sets just means the set of everything that's in both sets at the same time. We have an additional condition that has to be met for the quotient of two functions. We know that we can't divide by 0, so we have to eliminate any x values that make the denominator 0. So not only do we have to make sure that x can go into both f and g in this case, but we also need to make sure that the x we choose doesn't result in g of x being 0. So let's do an example. Let's say we want to have the functions f of x equals x squared minus 4 and g of x equals the square root of 3 minus x. Find the sum of f and g, the difference, g minus f, f times g, and then g over f, the quotient. And then it asks us to find the domain of each. Well, f plus g is pretty straightforward. That's just x squared minus 4 plus square root of 3 minus x. Not a lot of simplifying we can do there. For g minus f, we get square root of 3 minus x minus the quantity x squared minus 4. And then if we want to, we can distribute the minus sign through to make it square root of 3 minus x squared plus 4. F times g, not a lot of things we can do here. It's just x squared minus 4 times the square root of 3 minus x. You could distribute the square root of 3 minus x through that difference, but not a lot of point in doing that because there's not any other simplifying we can do past that. G over f of x will be square root of 3 minus x over x squared minus 4, the g of x over f of x. Well, we look at f of x equals x squared minus 4. Its domain is all real numbers. There's nothing that we cannot plug in for x. However, for g of x, I got to make sure what's underneath the square root is positive or 0, cannot be negative. So I know that if I put in 3 for x, I get 0, and I can put in anything less than 3 for x, and it'll be positive. So our domain will be negative infinity to 3 and include the 3. So the domains of f plus g of x, g minus f of x, and f times g of x will all be the interval from negative infinity to 3 because that's the set of the x values that's in both at the same time. For g over f, we also need to make sure that the denominator is not 0. So we see that the denominator is 0 if x is 2 or x is negative 2. So we need to throw those out of our domain. So if we throw negative 2 and 2 out of the domain, we get the interval from negative infinity to negative 2, union negative 2 to 2, and then union 2 to 3. The 3 is still included, but the 2 and the negative 2 are not. The other way that we combine functions is through what's called composition. So if you have f and g are functions, then the composition of f and g, so this is f composed with g of x, that's how we say that, f composed with g of x, that's equal to f of g of x. So what that means is that we would take the x out of f of x and replace it with g of x. So let's look at a specific example. Let's go back to those same two functions that we had on the previous slide. F of x equals x squared minus 4, and g of x equals square root of 3 minus x. F composed with g of x, again, by definition, that's f of g of x. G of x is the function square root of 3 minus x. And again, this notation tells us to replace x in f of x with what's in the parentheses. So we get the quantity, square root of 3 minus x squared, minus 4. And then when we square the square root, we'll just get 3 minus x minus a 4. And that simplifies to negative x minus 1. Now, with compositions, we have to be careful with what's going on with the domain. If I look at the final answer here, it looks like I can plug whatever I want into x. But remember, this is not how the function was originally defined. The function was originally defined as f composed with g of x. That means that whatever goes in for x has to go into g of x, and what comes out of g of x has to be able to go into f. Okay? So it's the set of x values so that x is in the domain of g, and g of x is in the domain of f. X can get plugged into g, and g of x can get plugged into f. So, like I mentioned before, it looks like the domain, if we look at the final answer, it looks like the domain is negative infinity to infinity. But that's not correct, because it has to be in the domain of g as well. Going back to g, remember its domain was negative infinity to 3, and so that's the domain of the composition function in this case. What I suggest doing when you're looking at domain of composition is look right here at this step. Right where you've plugged in g of x into f. And look at the domain at that step and see what can happen. Not after you simplify. Look here as you plug g of x into f of x. Okay. So the domain was for g was negative infinity to 3. There was no issues, and that's what we see right here, by the way. Right? This is the domain for g. I don't see any other issues, right? Whatever comes out of g can get plugged into f, because all we're doing is squaring and subtracting 4. That's what this means here. The domain of f was negative infinity to infinity. There's no worries. Okay? So we conclude that the domain just really is the domain of g. All right, let's look at another example. We have f of x equals 1 over x minus 1, and g of x is equal to x squared. We want to find f composed with g of x, g composed with f of x, and g composed with g of x. And then it asks us to find the domain of each. So again, by definition, f composed with g of x is f of g of x. G of x is x squared, so the composition is 1 over x squared minus 1. G composed with f of x is g of f of x. F of x is 1 over x minus 1. We plug in 1 over x minus 1 in for x into g of x, and we get 1 over the quantity x minus 1 squared. We can also compose a function with itself. That's what g composed with g of x is. That's g of g of x. G of x is equal to x squared. This notation again means plug in x squared where I see x, so I get x squared quantity squared, or x to the 4th. Let's look at the domains. Go back here. The domain for g of x is certainly all real numbers. The domain for f is anything but 1. So domain of g is all real numbers. We need to make sure that when we put g of x into f, we don't get a 0 in the denominator. That means our x squared cannot be 1. So that means that x cannot be plus or minus 1, so our domain is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity, and that goes along again if I scroll back. This is where we first plugged in x squared into f of x. So right here I would look and see what the domain is of this function right here. For g of f of x, we said that the domain of f of x was negative infinity to 1, union 1 to infinity. No matter what comes out of f, it can go into g because g of x is just x squared. So the domain is just what the domain of f is. Again, scrolling back to the previous slide, if I look at here where we've plugged in what f of x is, again, I can just check for what the domain of this function is, and I see immediately that I cannot plug in 1 for x. Finally, if I look at the last one for g composed with g of x, at this stage where we've plugged in x squared for x, I see that I can plug whatever I want in for x. We don't get any domain issues, so the domain will be all real numbers, which if I scroll back through the next slide again, that's exactly what happens, is that the domain is all real numbers. Let's do one more example. Rather than doing the composition, this example asks us to decompose a function. We have f of x is the 1 over the cube root of x to the fourth minus 6, and it asks us to write f as a composition of g and h. There are many ways we could do this. So let's look at a couple. Notice that one of the functions that I have, if I just imagine this thing as a big old x, one of the functions would be 1 over cube root of x. So if I let g of x be 1 over cube root of x, and then h of x be x to the fourth minus 6, I like to think of this as an outside function and an inside function. X to the fourth minus 6 is inside the cube root here, so that's what I'm letting my h of x be. My outside function is 1 over the cube root of something, so that's the 1 over cube root of x, which is what my g of x would be. And if you go through and do the composition, you see you get exactly what f of x is. Another way to look at this is that this could be thought of as your inside function, and treat that x to the fourth as an x. That's another way you could do it. Or, what I actually wrote here, I could think of this whole bottom as my inside function. The cube root of the x to the fourth minus 6 is my inside. And then my outside is just reciprocating 1 over x. And again, if you go through and actually do the composition, you see exactly what we started with f of x. This idea of being able to recognize an inside and an outside function is an exceptionally important skill when you get to calculus.